Hey guys, in today's video we are going to be considering the filament of a light bulb. Now, it's entirely possible that at this point in your lives, many of you have never actually had a chance to see the filament of what's called an incandescent light bulb. So for the most part, what you've probably seen lately anyway is either a fluorescent or an LED light bulb. So let me show you a close-up of an actual incandescent light bulb. Now, normally I pass this around in class, but obviously that's not possible right now. As you can see, the filament of the light bulb is the thing there, the little wire that looks kind of like a spring. This happens to be a burnt-out light bulb, and so the other end of the filament was supposed to attach, I think, over here, but it's way the heck over here because it broke. It burned out, as incandescent light bulbs were wont to do. I couldn't really hold it steady enough for it to not be, for the end to not be waving around like it is. So sorry about that. But the other part you can see quite clearly. It looks just like a spring. All right, now let's go back to that picture that I showed you there at the start. What this is saying, what this image is showing, rather, is that what looked to you like a spring is in fact what's called a supercoiled spring, right? So to your eye, it looks like, to your eye it looked like this, but what is actually the case is what looks like a wire is in fact also a length of, well, is in fact also a coiled spring. So to your eye, it just looks like a wire, but it's actually much thinner than it appears because it's a spring itself. I won't finish trying that out. So it's really quite a remarkable thing if you stop and think about it. Like, how on earth did they make that light bulb filament as thin as they did? And I have actually read up on the process. It was not easy, as you might imagine. In any case, well, we'll get started on this in a moment, but the filament is remarkably skinny. The other thing I wanted to show you related to that light bulb is some other feature that you may not have noticed before. Now, a lot of the time when a light bulb burns out, you might see like this gray on one side, and if it's a frosted bulb, meaning it looks sort of white instead of clear glass, you might not really be able to appreciate very well what this is. And actually, it's also hard to appreciate what that is in this video at the moment. So I took another picture of it so you can really tell what that grayish spot is. You might be able to see reflected on it my fingertip. My finger is not reflecting on the glass there. It's reflecting on the gray thing. Let me zoom in. Yeah, so it's reflecting my fingertip. What's going on there? Well, probably most of us have never thought about how you actually make a mirror, but what a mirror consists of is you've got some kind of a backing material, so like wood, or whatever, and then laid down, well, actually probably glass, and then laid down on top of the backing material, my illustrations are just not doing it with this stylus, is a very thin layer of metal. Usually it's silver. There's a number of good historical reasons why they use silver, despite the expense and everything. And then on top of that, they lay down glass. This stylus, I tell you what. Okay. And so then, when you look at it with your eyeball there, right, what you immediately perceive, of course, is the glass. But light that's traveling and hits the silver reflects off into your eyeball because the glass is, of course, transparent. And so that's how the reflection is formed, is on that very smooth silver backing on a mirror. Well, so what you're seeing here is tungsten from the light bulb filament, which was sublimed meaning sublimated, turned directly from solid to gas when that light bulb filament burnt out. It got so hot that it didn't just melt, it boiled. Well, it went past boiling, right? It sublimed, went all the way from solid to gas, and then the vapor deposited on that side of the glass for some particular reason. So I've saved this burnt out light bulb for many years for exactly this amazing phenomenon that I get to observe for both chemistry purposes and also physics, as it turns out. All right, so back to the original prompt. What we're trying to figure out, if you read through the question, is the uncoiled length of the tungsten filament. So as usual, step one is going to be read through the problem and find the numbers which are going to help you solve the problem. So read through the problem and pause me, read through the problem, identify the numbers that are going to help you, and identify the kind of a thing that they are. All right, now that you have done that, at least I hope you have, let's see, we have 60 watts. 60 watts is a power. Power is P. Okay, remember a watt is a joule per second, so a 60-watt light bulb uses 60 joules of energy per second that it's turned on. All right, then we have this number over here, which unfortunately the unit broke over there, so that's millimeters. That's the, got to be careful there, it says it's the diameter of the wire. Okay, all right. And then we have, let's see, it says the wattage of the light bulb is based on connecting it to 120 volts. I'll expand on that in a moment. And then we have this other number, there it is, the resistivity, it says. Now, a brief note on the 60 watts versus 120 volt thing. There really isn't any such thing as a 60-watt bulb. Mr. Erica, what are you saying? Are you about to shatter my entire world? Yes, I am. There's no such thing as a 60-watt bulb. It's only a 60-watt bulb if you run it at 120 volts. For that matter, you could make any light bulb effectively be a 60-watt bulb if you just ran it at a different voltage. The equation for power use that we'll be using in this problem is V squared over R. So the resistance of the bulb is probably a fixed quantity. That's actually not true. Light bulbs heat up as you use them, and as we discussed in a previous video, when it gets hotter, the resistance is larger, which is sort of interesting. All right, now, assuming that were a constant, though, which for many resistors R is a fixed value, if you take that given resistance, the amount of power that it uses is going to be larger or smaller depending on the value of the voltage that you use. Okay, so if you put more volts across it, it's going to use more power. Now, Mr. Erico, you might be asking yourself, what is power? Well, so here's a couple of things power is. Power is, we said, energy use, right? So for the light bulb, that means, first and foremost, it makes light. Light is a form of energy. Okay, so that's one place where the energy goes, right? Every second it's turned on, it produces a certain amount of electromagnetic radiation, which is to say light energy. The other primary place it goes, actually, for an incandescent light bulb, though, is sort of embarrassingly heat. There's a lot of heat in electricity, guys. I don't know if you have ever, done something as foolish as touch the casing of a motor that's been working really hard, but you could burn yourself on it, okay? Or for that matter, if you've touched the outside of an incandescent light bulb after it's been on a while. I've gotten many a burn throughout my life from accidentally touching such bulbs. Like, they get hot. And so that power use corresponds to a certain amount of heat being produced. Okay, now let's actually get on to actually solving this problem. All right, so here's what we've got so far. Power, 60 watts at 120 volts. Based on the other information we've got, it looks like probably we'll be using R equals rho L over A. Now, if you think you see where to go from here, again, pause me and just keep on going, all right? Um, so the goal is to solve for the length. All right, let's plug in what we seem to know. Looks good to me. Resistivity goes there for the rho. And then we're solving for L, the length. All right, and then we said the tricky, annoying thing is, and I did this because your book will do it, and so you have to be prepared for it, the diameter. Ugh. So don't plug in that number as is. You'll have to divide by 2. The other thing that you need to make sure you avoid is it's not 2 pi r. I don't know. Happens all the time. But in order to solve for L, we would also need to know R. And the resistance is not given. So sometimes people look at the power, the 60 watts there, and they will plug that in for the resistance for some reason. 60 watts is not a resistance, right? Ohms is a unit for resistance. You would have seen this after it if it was a resistance. So we can't plug it straight in. We're going to have to find it using one of our equations. Well, if we want R, and we have P, and we have that it runs at 120 volts, this is the one to use. All right, so let's go ahead and solve. And again, if you feel like you know what to do from here, pause me and do it. Okay, so now if we solve for the resistance, we get 240 ohms. If you got a very, very small number, you made an algebra mistake, since you're solving for an R on the bottom, that's the worst for algebra. Remember, you have to multiply both sides by R before you start dividing numbers, okay? And now we can plug into R equals rho L over A. Okay, so you can ponder that setup. And note that I have divided that diameter by 2 for it to be a radius, and I've put it into regular meters. And there we have it. The length is 0.55 meters, okay, or 55 centimeters, or 21 inches or so, which is kind of mind-boggling. That little tiny filament looked like it was maybe only a centimeter long, but if you stretch it all the way out, like all the way uncoil it from its initial super coiled state, you're going to have a filament that's 21 inches long. Okay, it's a surprising result, but apparently true. If you look it up, you can find out for, you know, whatever size bulb, how long is the filament. All right, pretty amazing. I hope that was helpful for getting you started on the homework, and let me know if you have any questions.